Welcome to this lecture 10, I think. Lecture 10 or 9, I can't remember now. Anyway, we are going to start with some kind of logistical information with respect to assignments and your project, and then migrate to what we were discussing last week, which I think we entered the NLP discussion. And today I'm going to plan to finish the embedding discussion that I started and I kind of left in the beginning. Then I'm going to go into simple applications of recurrent neural networks, especially simple language models, just to understand the kind of a block diagram and neural machine translation. And then I'm going to cover, I'm going to start transformers. So that's basically the plan for today. Okay. All right, so I haven't not presented assignment 4, I think, in this class. So this is your last assignment. The last assignment is, this assignment is different from the previous ones because, as you probably already have read it, you're not doing any coding, which is, I know it's a great disappointment. But from that perspective, it is easier than the previous ones. And I did this, I eased a little bit assignment 4 for this reason, because of this guy, because of the project. So I want you to focus on the project, make sure that you have a successful submission on the project side, and hopefully you will also able to do assignment 4, which is due April something, mid of April, something around mid of April. All right, so let me present it. This assignment, the aim of this assignment is also different than the aim of the previous assignments. In a sense, by the way, I apologize. I have some issue in my mouth and I cannot speak very clearly, okay? And my volume is also reduced today. But as I said, the assignment here aim is a little bit different than the previous ones, in a sense that this assignment is trying to teach you some systems level view of an AI system in operation. Obviously, an AI agent is far greater than this is only part of what is an enterprise AI system, where an agent is expecting to have some knowledge from domain knowledge from that enterprise. So typically, there is a lake house. Anyone familiar with lake houses? Yeah, lake house that stores lots of data, other structured or unstructured data that are coming out of databases and things like that. All sorts of data in the enterprise. And the lake house, the source of acts as its source for retrieval augmented generation, RAG, that is existing assignment around. So at the end of the day, I'm going to get a system level view of what a RAG system is and be able to answer interview questions that are associated with this system level view. All right, so for those who are not familiar at all what on earth a RAG is, so they have never done anything like that before, there is a link over here. Make sure you click on that link. Typically, many books in this O'Reilly is kind of questionable quality. Some of them, though, are pretty good. Okay, and specifically for the time that this thing showed up in the library, this is still good quality sort of product that covers the RAG pipelines and gives you an architectural level view, system level view of what a RAG is. I hope everyone is familiar with how to access it. Obviously, this is one of the key figures. I advise you to study chapter number 1 that has the various views of the pipelines. That I said the lake house kind of thing. There is an ingestion pipeline, visualization, some, I will call it a variety of databases are there, not only vector database, but also relational and graph databases, 3 types of databases you need to be familiar with, right? Then there is an optional kind of training pipeline because many RAG systems employ instruction. So the instruct dataset generation is due to the fact that most companies are using some other LLM, if you like, to act as a source of ground truth, and be able to tune their language models according to the extracted dataset they are building. Either they are building it because some external LLM is involved, or because their internal processes are revealing ground truths and they are annotating as they are progressing. That's a very common pattern these days. Obviously, the fine-tuned models may arrive into some kind of model registries, and then finally, during the inference, the knowledge acquired by this RAG pipeline is used to answer questions for the various things like customers. This has a universal application out there, and still quite a lot of companies are interested to this type of systems. So your assignment is asking you 10 questions. First, obviously, you need to click here and be sure to study both the GitHub repository. Out of the many RAG implementations selected RAG flow, there are many others, but they seem to have quite a lot of traction, and also they seem to have a permissive license. For the documentation of RAG flow and the documentation here and the code is going to help you to answer specific questions. Many of these questions are associated with chunking, like the concept of chunking. You will also read about that in the book as well, which is basically how we can partition, if you like, the text, whatever, in order for it to be converted into knowledge, like in terms of vectors and others. The chunking strategies, in other words, a set of questions. Other set of questions has to do with the retrieval. Retrieval is very important. By the way, I forgot to mention, someone can give me, you are starting it? Okay, good. The retrieval is obviously quite important. There is a re-ranking. We ask you a couple of questions about that and the retrieval kind of part. Because obviously you need to retrieve the right documents in order for to extract the knowledge when you're doing inference, and also the fine-tuning. So indexing and query understanding is part of retrieval, and then we have the knowledge representation kind of layer, where we ask you a question about how the knowledge graphs. So there is an emerging capability in the initial kind of RAG systems that they didn't have graph databases to actually incorporate graph databases, and probably you've seen similar things being quoted in the so-called context management of AI agents today. Right? Okay, so we have some data ingestion questions. In general, just 10 questions. The outcome for you is going to be up to 5 pages of markdown. That includes also the figures that you want to refer to. So you need to write it in a report, which is parsable in GitHub. Okay, so the only thing that the TA will do is click on that markdown file, and all the figures and the associated answers should be there. You can either write it in the form of a notebook, or you can write it as a plain markdown file. Just that any figures you refer to has to be parsable. It's just like anything. All right. Any questions on assignment 4? Hope you get something out of that assignment and you don't spend too much time on it. Don't spend too much time on it. Just read background reading effectively on your spare time, and I think in 2 weeks it's doable to submit something. Now, I want to spend some time on the project. Who has started the project? Okay, this is not good. I will tell you that from now. It's going to be probably, this is the time that I asked the question to myself, how much time do I need to implement the project? I need definitely a week to even familiarize myself with the code base. Okay, like when I say a week, I know you have, let's say, 5 other courses and 5 other assignments and 5 other things. Like if you assign it, like if you have a weekly assignment every week, like the title of week number 1 will be what is going on. Okay, just what is going on. You can use, I know you're using coding agents to understand what on earth is going on, right? But even the coding agent will have some time, and you also have to always review what it tells you. Okay, so 1 week. Second week is I need to solve the alignment problem. Okay. If you are lucky to solve it in 1 week, that's fine. That's 2 weeks. Then you have to solve the derealization problem, 3 weeks, and then you have to solve what else? The cloning problem, 4 weeks. And so you're already looking at 4 weeks. And so I told you there's no, the assignment is due May 3rd. So there's no really time to waste here. So start it, take advantage now that the semester is in a better shape than it is at the end of the month in terms of stress. Okay, so that's basically it. So let's start what we did earlier. Let's see. Yes, go ahead. I don't think that you need a GPU for this. The reason why, or even a GPU that it is collab-like is going to do okay, because at the end of the day, it's audio, in a sense that, you know, most of the tasks are associated with audio, and most of that, as I said, if you follow my advice to chop off a video in, let's say, into 5 minutes and not process like 1 hour and a half the interview, you can actually do the processing just for the clip. Do it offline in the sense that you can use even your CPU to do the transcription and things like that, and run all the stages. Yeah, you will wait longer, but there's nothing I can do about that. Those within the Mac platform, they should get some acceleration. I don't have the Mac platform, so I do not know. I'm expecting you to get on with it, to provide some kind of feedback in the channel about what is happening, right? And help others. It's not a zero-sum game here, right? So if you have a Mac or you have Windows and you have some acceleration capability there, just let us know. We are, unfortunately, because of the, we are swamped with tickets, especially after we provide grades back, we're swamped with tickets. I should also mention that. Can I have 1 point? Can I have 1 more point? Can I have 1 more point? And I say you are missing the big picture here. Because most of the responses are like this. You are missing the big picture here. If you are spending time to argue about 1 point of 1 assignment that is total 0. Has a weight of 0.3 in the total grade, you are missing the big picture. So try to prepare for the final exam. Make sure that your notes are in the second half. We are going to enter now some difficult discussions in reinforcement learning. In Markov decision processes, the material is not easy to follow. Try to follow that, and don't spend time on winning 1 point of the 1% of the 30%. All right, so this is what we did, I think, last time. So we went over the RNN kind of discussion. The RNN discussion. So if I am to ask you the following kind of question, what was the 1 reason? If you are to mention 1 reason why we entered this discussion, what would that reason be? The most dominant reason why we had to change the architecture to a recurrent architecture, what would that be? Yes.
Long-term dependency.
Well, okay, so someone could mention, the fact that we have flexibility. The reason is like a combination of two things. One is memory, and the other is flexibility in terms of input, right? So because effectively we can define whatever sequence we want, and we can actually process it with recurrency without necessarily having to fix, like we did with dense networks or convolutional neural networks, this input size. And the same thing can be also discussed about the output as well, because in general, with recurrency, we can implement sequence in, sequence out, or sequence to sequence kind of model, as we'll see later today. So we went ahead and I changed the sigma to tan h. What is the reason of this change? What is the reason? Because over here we had something that was going from 0 to 1. And as I said, not a good idea to have something like that in a feedback path, in a feedback loop. Okay. So we went from -1 to +1 with a tan h. Okay, so other question. We saw an application where we was an asset price kind of application, but someone asked us to implement the price of the next trading day given 50 previous prices. We recognized that this network needs lots of iterations in order to build a predictor, because obviously this has parameters, right? So we use thousands of time series, right? Thousands of time series. I don't think, I think I put a notebook in your website now so you can actually see it, right? This specific notebook that I was referring to last week. And finally, we built a predictor using this RNN. The RNN was obviously a single euro, so it was producing just a scalar value that we call a hidden state. And we recognize the fact that we need to build a network that it will support vector hidden states, because intuitively we will imagine this vector hidden state to include many latent factors that can affect the price of the asset. So we went ahead and we did it. We went ahead and we created this kind of layer. And as it turns out, this layer is very similar to other layers we have seen earlier in this kind of class. More specifically, the fully connected dense layers, except obviously the nonlinearities are actually different, and obviously notably the previous hidden states are considered in the output of future hidden states. Everything is straightforward, I think. It's not really a major kind of change for us, especially after we have gone through. And we also had some kind of intuition and some kind of intuitive discussion as to how do we come up with the number of neurons that we need in a layer if we had some kind of domain expertise associated with us. Otherwise, it's almost like a black box, just like what was earlier. So the domain expertise that we had is that, looking at a kind of time series of price fluctuations of a stock or a commodity, we definitely see some kind of a negative correlation of prices between going on as a structure in what's called the covariance kind of matrix. And this negative correlation simply translates negative exponential correlation is typical. Simply translates into an argument that two trading days which are next to each other have much higher correlation compared to two trading days which are far away from each other. And we kind of use the singular value decomposition to pick up the most important latent factors out of the data that someone gave us. So we had 10,000 columns over here because someone gave us 10,000 sequences over 50 trading days each. And out of this decomposition of a 50 by 50 kind of matrix, we're able to plot the spectrum of the singular values and select the ones which are important. If we see a spectrum like this, that kind of makes some sense. So the other thing that we covered is that the fact that we have obviously, if the hidden state is a vector, now we also have still predict a price. So we hit the hidden state with a head at the appropriate time where prediction is required. Let's say at the time is equal to 49. We hit the H49, which is now a vector, with this kind of head to match what we want, a y hat, which is a price, with the hidden state. So this was a regression branch, so to speak, right? And dimensionality matching happens through a well-known to us now tool, which is a matrix by vector multiplication. That's the projection part. Evidently, if we have classification, obviously we need to look at the number of classes over here to do this dimensioning, right? As we'll see in language model, this dimension is not doing projection, but it's doing lifting. And arrive at the posterior probability of all the possible classes that we have in the problem. Any questions on this head? Okay. All right. So we then answer the question: what finally determines how much long back we can go to account for the fact that input data may affect the output? How much earlier can input data can affect the output? And the answer to this question was, what was the main driver on the answer? The understanding of how gradient flows through this recurrency. So gradient flows from the top, where losses are obviously observed, to the inputs of the network, but the inputs are 50, 100, 300 stages that this recurrency is implemented. Who determines the 50, 100, 200, 300 stages? Our problem. Okay? Sometimes someone will give us a sequence which is 300 tokens long. Sometimes they'll give us a sequence which is 50 prices or whatever. Okay? So the same question applies. How much we consider the inputs that happen 100 stages earlier to the formation of the outputs over here, which defines the losses of our prediction. So we went and looked a little bit at backpropagation, and we kind of recognized the fact that it's really this W matrix that defines what's going to happen in terms of gradient, right? And this matrix W, the composition of this kind of matrix W may be such that either the gradient will explode or diminish. If it is exploding, we can clip it, but still not good things will come out of it, as it's also explained in the input current kind of book. If it is diminishing, which is typically the case, means that the gradient backwards, because this gradient flow over here will be reduced. Still, we may get something out of here. We may, and I say may because we may not need to do prediction every single input, but we only need to do predictions at the end, like in the pricing problem that we were facing. Only do predictions at the end after we observe the whole sequence. So this branch may not even be here. So if this branch is not here, the only loss we form is at the end when we observe 49 prices, and then we say, okay, what's the 50th? So if this is not here, you get some gradient here. In the next instance, this guy will create a smaller gradient and a smaller gradient and a smaller gradient to feed back. And what is the impact of that? Well, remember, gradient is the main reason why parameters change. So for that specific input that happened 10, 20, 30 times earlier, right? This stage is kind of earlier, our adaptation of the parameters of those will not be there. Parameters will not change means that effectively that the RNN is shortened in terms of capacity of absorbing sequences. And of course, bad things will happen in terms of prediction. So if you have a problem that requires some really short memory, it's okay. If you require problems like natural language and others that require some long memories, That's obviously not okay. And the solution to this came from the long short-term memory architecture that we didn't explore. We didn't spend a lot of time on it. Because even that one turns out not to solve the problem, as evident from the transition to kind of transformers. But mainly the bottom line and the key differentiation of this memory LSTM kind of network is this line. This line is the one that carries, if you like, the long memory, as I called it, which is basically the vector S now. And effectively, the architecture works in two modes. One is, okay, can I determine what I need to remember and what I need to forget from either the input or the long memory or the output into the next stage? And these are the responsibility of the gates. And the other is make sure that this I have something to preserve over many, many stages, because over here, I will be storing for every instance of the recurrency something. Okay, that's basically the S, also known in the literature as a cell state, which you don't need to remember, just tell you. So this was basically the LSTM architecture. I hope you watched the video, some of you at least, I hope. I advise you to watch one of the videos in the website to understand a little bit more with animation what's going on. And then we went into, okay, fine. We saw some architecture that to prepare some of the discussion kind of today. And then, okay, we will use this architectures in these two tasks, language model and neural machine translation. But before these architectures are able to process anything in terms of natural language, we needed to understand a little bit about tokenization. And we needed to understand also about embeddings. What is the embeddings here? I haven't even written it down somewhere. Someone is supposed to write the embeddings over here, but it doesn't matter. So what was this kind of tokenization discussion? So tokenization is, anyone? What is a tokenizer? What is on earth a tokenizer is doing? Yes? Anyone? Yes?
It gives us the vocabulary.
It gives us the vocabulary. That's the only one answer. It gives us the vocabulary. Every single language model will have a finite vocabulary. We call it the set V, capital V. And the job of the tokenizer is to give us the vocabulary. And we will use an algorithm called byte pair encoding to come up with a vocabulary over multiple iterations. I told you one page was not working at the time. And since then I fixed it. I'm not sure if you saw it, but let me sort of go over now this page. Which is in your LLMs, text tokenization. The tick tokenizer. The tick tokenizer web app. I told you that we will use it. Hopefully it will work over here in this over the computer. That is, so for example, so that's the end result of tokenization. We have some Python code and we copy and paste it in the input field over here. And the tokenizer works in the web browser, which is VB tokenizer, converted the input into tokens. And the token that we selected is a very initial kind of token that existed years ago, called the one that was used by OpenAI to release GPT-2. Okay, and the resulted into 186 tokens, which means my vocabulary size, if this was the only text that I would have for the specific vocabulary that the OpenAI kind of defined, converted this into 186 tokens for this specific. So what we can do now is you can say, okay, fine, let's change one. By the way, GPT-2 has a vocabulary size of 50K. The vocabulary size was 50K for GPT-2, and later other models, more GPT 3 and 4. The moment I changed GPT 3 and 4 tokenizer, right? The number of tokens went from 186 to I think to 149, right? Any intuition behind this? Any intuition behind the fact that we have now a small number of tokens? The vocabulary, by the way, is now larger. That's where the intuition should be based. The vocabulary, I'm not sure if you read over here, it's possible to read on the back. It's 100,000 now tokens instead of 50, yes.
What happens if that's not in the vocabulary?
Sorry?
If there's that's like not in the vocabulary.
You have, as we discussed, we're going to have an unknown tag there in the output. But, and I don't have the vocabulary in front of me, but without any doubt, there will be an UNC token over there. But yeah, what is the intuition of reducing number of tokens because the vocabulary now is larger? Yes.
What combination of characters
So the intuition is exactly the same as happens to us, right? I mean, when I am an excellent speaker of English, which I'm not, but let's assume that I'm expressing now, I am devastated. Devastated, the word devastated, right? Someone who is not as good in English as I am, what will try to do, not to express the same thing, what they will do? I'm very sad, they say. I am very sad. Very sad versus devastated. One word, one token versus two. Okay, so that's the intuition. Very simple intuition. Okay? Which means that the context requirements for a tokenizer that is not as rich, right, is larger. Okay, this means that this LLM with the same power as the everything else being equal, they will actually hallucinate earlier. Because the requirement for the context is larger. The other thing actually is happening is that there's a trade-off though, because the number of tokens is smaller, but the vocabulary size is richer. This means the V by D matrix is larger in general. Okay? So there are some trade-offs in terms of complexity versus performance. That is the only thing, which is obviously always the case in any engineering kind of choice. You can read a little bit about this over here in the two paragraphs that follow. So we went into the discussion of what comes after the tokenizer. And what comes after the tokenizer is the embedding device. The block that it will do will take the token, the integer numbers, and will convert it into a dense vector. And I showed you an image from TensorFlow projector where those dense vectors were visualized in a 3D space. Do you remember this image? Right? The smaller d was 200, but we were able to see them in the 3-dimensional space. And we went through the reasoning, what makes a good embedding device. And the reasoning is that I want neighborhoods, right, to capture similar meanings. Okay? We all recognize why the trivial one-hot encoding will not want to carry it. And because the dot product there will actually be 0, right? While we want the dot product to be very large, right? Even though, of course, we are normalizing with, so we are looking at hyperspheres now, we are normalizing the lengths. The cosinus theta between two vectors that carry similar meaning is a large number, it's close to 1, right? So you can get the dot product to be a large dot product. And with that said, I kind of went into the website and I suggested what will be the inspiration for us to build an embedding device such as this. Anyone remember the inspiration? What is the inspiration? What was the inspiration? A week ago. the inspiration was that I came from a linguist that said the meaning of every word that we meet in a sentence is probably determined with high probability from when we see frequently around it certain words. For example, the meaning of the word bank is going to be the institution when we see next to it an account or money or something, right? And it's going to be completely different from if we see the word bank next to it to be crocodiles, I mentioned. This second bank is going to be associated with the river. Right? So we are able to sort of convert the problem of embedding generation into what is known in the literature, in general in AI, and also in self-supervised learning, a pretext task. So pretext tasks are tasks that we use in order to do something else, not the task itself, but get something out of it. So by converting the embedding generation into a prediction pretext task, we are suggesting that if the embedding is the right, if the embedding of bank is the right one, then the words that are going to be predictive next to it are going to be the ones that agree with ground truth with high probability. So if I have text about that my bank account is whatever, has interest rate of something, right? Or the interest in or this bank account is 9%, whatever, then we will build an embedding device that is able to predict successfully the account and the interest. So this is what I'm going to do. So let's try to see how this will be done. So I kind of drew over here the block that we are going to build. The center word is coming in, bank. And then at the output, predictions of what surrounds bank with high frequency, he said, right? Therefore, these predictions come in the form of a probability, right? Which is posterior because I'm giving you the center word. So we are in familiar ground, so to speak, here, right? We are always in this course building P models that are producing P of y given x comma w. That is what we were doing forever. So something here is the x, something is the y. What is the y? Well, the y is obviously the surrounding words, and the x is the center word. Nothing changes, just notation. So over here, there will be a P model that we are not going to get out of the P model the representation, but the representation is going to show up inside the P model. It's going to be built, as I said, a pretext task. We are building something internally to show up in the outside world a good prediction. So let's see. So this is a lecture 10. This is the third. So we'll continue on embedding. Okay. All right. So in order for us to build a PIMO, so basically the idea is to build desk approach. prediction model that internally forms representations that have the properties we need. Okay, and the other thing, this is the definition of a pretext approach. And the other important thing I need to mention is the context-free representation. These representations of our vocabulary tokens will be dense vectors, but, and this is the important thing to recognize, if I draw the d-dimensional space here, which is evidently the three-dimensional kind of space here, and I kind of tell you that right now I'm getting a representation of the token bank if I feed Yahoo Finance throughout the training process. I feed Yahoo Finance, I get this vector as the representation vector for the word bank. That's basically what I aim to do, right? But if I feed National Geographic, right? I am going to get another vector over here for the word bank. I hope you agree. But in general, in building language models, right? And I'm not feeding only one part of the internet. I'm feeding the whole internet. So if I feed, let's say, to make a long story short, Wikipedia English, Wikipedia EN, right? In throughout, then I will get a vector representation that effectively is the average of all meanings that are embedded inside this Wikipedia. At the end of the day, out of this construction, there will be only one vector for bank. Irrespectively, if bank was in some sentences in Wikipedia, the institution, or the river. That's the definition of context-free representations. As we will see later on, we will need to build contextual representations, and there we will use the transformers. But we need to be able to distinguish between the two because they are sometimes used interchangeably in this industry. Okay. Yes.
Could you explain that real quick again?
Yeah. So what I'm saying is that you can follow the premise that Perth provided. Says, okay, build a predictor that's able to predict the words around you. But we only limit the discussion now, the input data. You remember the training data, right? The training data where I gave you an example for the training data over here. So we feed as training data only Yahoo Finance. The words around it, I mean, this system never saw any crocodile in the life. Okay. So only saw accounts, interest rates, and companies, whatever, right? So throughout this kind of this training data were only about finance, then bank will be in one point in the d-dimensional space. If on the other hand, I only feed National Geographic, they will be in a different point. But if I feed both of them, or in general the whole Wikipedia that has both, then it will be in the third place, the blue one. And effectively what it means is that that place that it is right now, the word bank, at the end of the training process out of Wikipedia will be the final destination, so to speak, because at the end of the day, we will, unless we do something very specific, either we have a National Geographic business or a finance business, we can build specific embeddings for our industry, right? But in general, we don't. We are trying to create sort of to process the whole internet when we're building language models. So we want to follow this blue. We're going to have only one blue vector out of the word bank, token bank. All right, so here's the training data. Let's write down the training data. So obviously, you saw the training data. Very trivial to get training data out of this. So we have P data hat distribution, which I hope you remember from the Vapnik diagram. We have W, T minus C. I do not want to use the word context here, although in the literature, in the original kind of paper, the window over which we are observing the surrounding words was called context. It's very confusing. I will call it window. Okay? So despite the fact I'll use C as an index over here. So this is W, T minus C plus 1, comma, dot, 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 comma, W, T plus C. I hope you recognize these are all the words surrounding words within a window size of 2C, given the center word. So this is the center word. And these are the window words, the surrounding words within a window. That's my P data hat. Again, trivial to obtain, as we discussed last week as well. Now, what we have learned out of this course is that our P model, what it should be with respect to P data hat. Far away or close by? Close by. Thank you. For a moment, I got really worried. So the P model, to be close by, should has the same functional form as P data hat. It should have a lot to do with P data hat. So I'm going to claim that I want to build a P model that is going to be, here's my P model. WT minus C, comma, dot, 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 WT plus C, given WT, comma, theta. That's my P model. Instead of W, because I'm using W for the words, I'm using theta as the parameter, the set of parameters. Same thing. Okay. So if I look at this P model, however, over here I may have 4, I may have 8, I may have 100 surrounding kind of words. And each one of these words live in what dimensional space? I want to take the W's and map it into a Z. Remember the notation that I'll be using here, right? That is my, I need to build some, this Z is going to be present over here, right? Inside this network that I'm going to be building. So these words live in the three-dimensional space. Do you remember from tokenizers, the sizes of this three-dimensional space? 100,000. 100,000, comma. Remember the conditional probabilities kind of sizes, right? Just to, and also remember what we were discussing about hidden Markov models few months ago, right? So 100,000, comma, 100,000, and 100,000 all the way to whatever my window size is. That's a huge conditional. So what I'm going to do now is similar to what I have done earlier. I'm going to take out of the hat an assumption, and I'm going to use it to simplify it. Okay, and this assumption I'm going to be using tonight is called naive Bayes assumption. Okay, so I'm going to explain it. So What is an A-based assumption? I'm going to put a box here. Given the center word, all words in the surrounding window are independent of each other. This allows me, remember the concept of conditional independence, or in general, the independence allows us to factorize probability distributions, right? So what we can write now you can, if someone asks you, you can factorize now the P model to WT minus C given WT comma theta. Can you do that? And the answer is yes, I can. Dot, 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 dot. Multiplication, right? Or equal to product from J is equal to minus C to J is equal plus C, but J not equal to 0 because 0 is the center word, right? Of P model of WT plus J given W P comma theta. As a product of the individual now conditionals. Now, in my P model, I only need to predict one word. However, the product is still there and will have significant implications to the architecture at the end. We will see that, right? So, but at the end of the day, I'm decomposing the complicated P model into the product of individual P models. Each P model will have to take some form now that will stitch things together because there are some dependencies which is not evident in the equation. So remember the maximum likelihood thing that I'm bothering you since we met? According to the maximum likelihood principle, we had arrived at a very general loss function. Okay. We started with Gaussians, and finally we evolved into conditionals, where our y and x's were there. Similar, we have y and x's, as I explained here as well, such that the notation is different. So the loss, so let me write down according to the maximum likelihood principle. We are optimizing according to maximum likelihood. Remember this famous loss? I think it's worthwhile cutting a piece of cardboard and putting the loss in the mirror in the bathroom when you use each morning, so you can always remember it. It comes very frequently in interviews, in places, of course, that is worth interviewing, and other domains, other places. Okay, so it's minus. Remember the form minus expectation. There was an expectation operation over what? Okay, well, it's not expectation over what, but definitely there is a log, definitely, so I will take it. Log of P model of y given x, comma, theta. That was the formula. If you go back to the website where the maximum was discussed, that was the formula. We did it in the regression discussion and in classification after that. Okay, but expectation over x comma y, it was written there, right? According to P data hat. This is a famous formula. everything we do in NLP, computer vision, whatever, is to some degree, okay, connected here. So what the formula said in English, just to recap, the formula said that effectively I'm optimizing, I'm trying to minimize this loss. That has a lot to do with some average risk, and the risk is the log of my y hat, because the P model is providing at the output y hat, my prediction. So across all data that comes out of P data hat distribution, all training data that comes, someone gives me, that is produced out of the P data hat distribution. So the X's and Y's are going to be examples over here. That's why we call it the supervised learning. Obviously, if we don't have supervision, if no one gives any data, but here they do because it's trivial to obtain, so we are stupid if we don't use it, then the losses are changing. The loss is going to be completely different. But for now, for us, for our nice environment over here, this is the one. So we will plug in now the X and Y and the P model. So we are going to have equal to minus expected of expectation of the, where, what is now my X and my Y? The input is the center word, right? WT plus J, correct? According to P data hat. Log of the product from J is equal to minus C to J is equal to plus C, J different than 0, of the P model of WT plus C, given WT comma theta. Let's now draw something that it will implement this. Input, we know. Let's define a capital W now matrix that it will compress WT down to Z. So this Z is Z that we need, the dense vector with D dimensions. And then out of that Z, I said, if the representation is correct, then the predictor is going to predict the words that are frequently next to that center word with high probability, right? So how do you build a predictor if typically what you had at the end is you had some kind of a head, right? It was before the spitting out the white hat. What was that head was doing? It was picking up the features, right? It was picking up the features. Are you following? You're in the dense network architecture. I'm referring now to function and NIST. We did function and NIST, if you remember. When did we do that? When we did the multi-class classification discussion, right? Where we had a number of layers, right? That was forming features one after another, H's we call them, H1, H2, H3. At the end of the day, we had the head. So we were done with feature generation, the body, and then we were hitting the features with the head, which was doing what? Combining the features, right? And then pass, not linearly, not nonlinear, linearly, and then passing it through what? S, starts with S. Softmax. Okay, so if this is my representation, the feature vector I want to form, right? I'm going to pass it through, let's say a W prime matrix, which I will qualify now with a J index, because J is present over here. Where is it? Yeah, over here, an index. So one of my P models I need to implement is WT plus J given WT. WT plus J given WT comma theta. So I'm claiming that if I have a lifting matrix in my head, in the head, right? Why lifting? Because at the end of the day, what I need to implement, the head was always doing dimensionality matching. Now the dimensionality has to, the predictions, the dimensionality of my predictions has to be D-dimensional or V-dimensional. The prediction has to be D or V-dimensional. V. So I'm D here, I need a lifting matrix. Not an embedded a projection matrix, a lifting matrix that will increase the dimensions of the output of the matrix relative to its input. The projection matrix always projects a three-dimensional point down to the floor. Lifting matrix picks up the projection and lifts it up to the three-dimensional space. Pass it through the softmax. Produce y hat j to be compliant with our notation. So this guy is V-dimensional. This guy is going to be V-dimensional as well. What output do we expect to see after the training is done? Let's assume that I'm only building now a window size of, we'll just look only at the prediction of it's just a single surrounding world, not many, it's just a single surrounding world. So do I expect to see the posterior probability distribution across all tokens, right? To be a discrete, obviously. So I'm expecting to see lots of bars, right? Lots of small values, and one value larger than the others. So if training finishes, right, I'm minimizing this loss, which means that if the center word is, as we did last week, if the center word is car, I typed car in the TensorFlow projector. In the neighborhood next to me should show up the word driver. So this thing here, this index of the winning posterior is going to correspond to driver. Bump will be one of those small ones. Nothing to do with car. Or maybe they do. They have to do with everything. So this is basically our y hat j, which is the probability wt plus j given wt comma theta. And then we put a star there to indicate that after training, this is going to happen. During training, anything can happen. What happens during training in the D-dimensional space? The car, as a point, I drew previously in the D-dimensional space the token bank, but now the car as a point changes all the time, position, moves around. At the end of the training, during training, gets closer and closer to things like driver, vehicle, things like that. It stays there in that neighborhood. Train will actually be close to car because there's also car of trains in trains, right? So we have the again the averaging effect of meanings that I pointed out with bank earlier. And the question is, are we done? No, we are not done because apparently we have this guy over here, which obviously becomes a summation. And now we need to predict the next word, the previous word, 2 words before me and 2 words after me, if my window size is -2 to +2. Okay, so I need to also provide predictions for those words as well in the architecture, right? So one center word comes in, 4 arrows, 4 white hats should come out. Where are the remaining 3? What should I do? All right, let's see. We are claiming that if Z is the right representation, we are claiming that if Z is the right representation, that same Z, if lifted via Wj prime, will give us the prediction. But at the same time, if lifted by another kind of matrix, it will be allowed to give us one word after that, the prediction of this. So this guy will actually be another zero distribution. And now this time, vehicle will show up. Vehicle shows up at the same time as driver shows up. Because, look at the architecture. This guy will be fed to a loss. This guy will also be fed to the loss. Because we're doing 4 predictions. There are 4 predictions defining 4 terms in the loss function. There's a summation in the loss function, if you notice. It's a product, log product. So I am picking up a loss from this prediction, summing it to this loss of this prediction, so on and so on. And I am coming up now with a gradient, stochastic gradient descent, who is going to update as theta, right? All of these matrices, this guy, this guy, this guy, and other 2 which I'm not going to draw.
Why do we need different matrices if we assume that the surrounding words are independent of each other?
Because the different they are not one point. The different lifting matrix will put it in the neighborhood, right? But it doesn't have to be, it's not the same matrix. Because only the safe only one matrix, if you give it one Z, it will put it in the same point. So vehicle and driver will end up in the same point if the matrix is the same. So we need different matrices. To build a neighborhood, we need different matrices. The neighborhood again of the predictions, the neighborhood of all my vocabulary will be something different, of course, right? Yeah, different point cloud. So in terms of equations, Z is in this kind of architecture will be WT transpose W, and all obviously will be D by 1. ZJ prime. This is the ZJ prime. The output of the Z by W prime J. The Y hat is my softmax of ZJ prime. And the loss is the cross entropy loss. And my theta is W times the comma, W J prime, comma, dot, dot, dot. How many matrices are there? As many as my window size. If I detected my window size. When theta becomes theta star, training finishes. When training is done, theta becomes theta star. And therefore I have here W star, W J prime star, dot, dot, dot. By looking at the architecture, can someone tell me, am I interested in all these matrices or only one? And the answer is only one. I'm going to have interest only on W star. I don't need only the matrices. The matrices are going to be trained, of course. They need to be there to implement the prediction and drive my losses. But the training kind of process will reveal to me the W star. I'm going to pick this W star and store it in Hugging Face Hub. Because I'm going to attach to it some metadata, Wikipedia English, and every time I have Wikipedia English as my training kind of data set, I am going to download it and use it as the embedding matrix. So W star, not with underscore, it's a matrix, is going to be a matrix of B rows and D columns. So if I store this Hugging Face Hub, am I able to retrieve it for a future embedding generation of this vocabulary? And I will get my embeddings via this operation here. All my Z vectors of my vocabulary can be obtained out of this operation. With W being now W star, the fixed matrix, fixed space, frozen, whatever. Having said that, probably you notice something there is the following. The WT, remember, the WT is in the three-dimensional space, it's a one-hot encoded vector, and we try to create a dense vector out of it. Well, is there any point to multiply one-hot encoding vector with a matrix? Is there any point? And the answer is obviously no, because most of the elements of that vector is zero. So all of the operations will be zero except from one. So equivalently, I am going to, for the word car, this is the index of the token car in my vocabulary is this row over here. I'll go look up the row, pick up my d-dimensional vector out of the matrix W, and get done. Are we following what's happening? So every token comes in, look up, get your embedding, proceed with your language model, who is going to do now the probabilistic modeling of another equation. Right now, all these equations I wrote is for representation learning. Okay, so let's see now what kind of simple, pretty straightforward language models we're able to build because now we have the dense vectors to feed into them. The trivial language model is going to model the p-model of WT given WT minus 1, comma, WT minus 2, comma, WT minus capital T, comma, theta. Now the question is different. Here we see the so-called next token prediction p-model, where someone is predicting the next token given a history of previous capital T tokens. I hope the question is straightforward. So we will use LSTMs, but I'm not going to write LSTMs. I'm just going to write RNNs in the block diagram. And I'm going to build now a very simple trivial language model that is going to implement this equation. Out of this language model, we'll revisit it a bit later and define the transformer-based language model, right? But before that, we need to introduce another task for neural machine translation before we go. So this is RNN. So I am going to have the unrolled architecture. In other words, I'm going to plot, just like I did for the price prediction, I'm going to plot the RNN in multiple instances in time, capital T instances in time. So I am going to have the RNN equation effectively, which is going to be fed some hidden state from the previous stage, H T minus capital T minus 1. And also as input, this embedding device we just built is going to accept an input token W T minus capital T. And this is obviously in the V times 1 space. This guy will be X T minus capital T. And this will obviously be in the D times 1 space. We just built it. And we are going to, out of this hidden state which is being formed, H T minus capital T, we are going to attach to it a head who is going to do now lifting to give us a V-dimensional y hat. So in the next stage, I'm not going to plot many, just we are going to receive WT minus capital T plus 1, X T minus capital T plus 1. The head is going to spit out the y hat T minus T plus 2. H T minus T plus 1. Mind the indices, right? Here, we are predicting out of this hidden state the posterior probability of the next token. And the next token, dot, dot, dot. X, T, sorry, W, T minus 1. H T minus 1. Head. Y hat. You tell me. Y hat of what? T. A trivial construction based on everything we have done earlier. The simplest possible language model you can construct. If you go back several kind of years, Andrei Karpathy built this RNN model while he was studying in Stanford, and he was basically dealing with a character-based vocabulary. And the notebook is also on your website if you want to take a look. So we are predicting next character, and the next character, and next character. I give you an input text. The language model is trained. During initial training, the prediction is pretty crappy. After a while, when you run it, you will see it predicts exactly the next token after a few iterations. Using plain old RNNs. Same principle we'll use a bit later for the more complicated language models. In my YouTube video, there is some more discussion about this. If you want to watch it, there is some kind of discussion about training and some kind of windowing that happens and resetting of gradients in backpropagation. But because we have replaced these RNNs with more advanced kind of models, then there's no point of you to watch that. But in case you want, it's there. So I'm going to move on now from a trivial language model to a trivial neural machine translation model. Okay. And this is the end of the modeling kind of discussion with the trivial as the headline. These models are also known as sequence to sequence. And you all use it every day. You probably notice that every time you type something on your phone, several icons pop up when you message. In iMessage, several icons pop up. And these icons are related to the words that you type. I'm coming home, there's an icon of a house popping up, right? That's an instantiation of a sequence-to-sequence model. Some input text is coming in, icons are coming out, and the phone is selecting which ones to show you. So over here, I'm going to deal with language translation, a use case. So we have, let's say, an input source language, which obviously you will not understand. That's an input language, foreigner language. And the task is to translate it to English. Okay? So the output, obviously the example is trivial. And it's kind of trivial in the sense that you selected, there are several complications here. Your website has some kind of discussion about Hungarian and English and more elaborate kind of notebooks. But here we have 1 to 3 tokens in both input and output languages. So we'll call these tokens as x1, x2, x3, and x1 prime, x2 prime, x3 prime. We use the notation in order to see how these tokens are fed where in the network architecture. So the premise of sequence-to-sequence models is that we will have an encoder and a decoder. So what the encoder will actually do, the encoder will encode the input foreigner language, let's say, and will form a hidden state, and that hidden state will be fed to the decoder to do the translation. Okay. And very much exactly the same principle happens in your project when you convert from English to Spanish, but obviously the models are more elaborate. So I'm going to build the block diagram. Nothing to, I'm going to super simplify the block diagram. I'm not going to be plotting any heads or anything like that. These are all assumed that are present. So some kind of initial hidden state is fed to first stage to form H1. Second stage, and when we say stage, meant we are using recurrent neural networks to, again, these are again the unrolled architecture. So some people are surprised why I wrote X3, X2, X1, not X1, X2, and X3. I'll explain that. In terms of notation, many people designate the H3, which is the last hidden state of the encoder, the thought vector. And magically, out of this thought vector, all translated tokens will show up in the decoder. Out of one vector, all three translated tokens will show up. We didn't spend time cataloging all special tokens that we have in NLP applications. One of them is the start of sentence, or SOS, as it is designated. And it's going to be used here to drive. Let me delete the thought vector here because I need the real estate space to do certain things. Actually, let me also move this box. So during training, I'm feeding the ground truth. I have pairs of source and target language. There are many data sets of this, obviously, available. So I'm using one of them for the specific source and output and target languages. But I'm starting the process with a so-called start of sentence token that evidently will better predict I as the target token, as the translated kind of token. A hidden state will be updated. And the next token that comes in is X1 prime. The output is going to be associated with the prediction of love, right? The third one is going to be input X2 prime and is going to predict ideally you. And finally, and I'm sure I ran out of, oh, I didn't. Okay, that's great. X3 prime comes in and end of sentence token is coming out, designating the end of the translation. So I drew the encoder, which produces a thought vector, and the decoder, who did the translation. there are a couple of things I want to mention. As I told you, I need to explain some rationale, some intuition as why typically you are feeding the input language tokens in reverse order. And this varies from source and target language kind of combination. Many languages, especially European ones, or Western Hemisphere ones, whatever you want to call it, they were always, the first token is with a very high probability associated with the subject, and the translation also found itself in position 1. So remember what's going to happen now in training. I want to kickstart the decoding process and translation process from, I will call it a place that during the back propagation, right, you have the gradient. The first token is always going to be the last token is being fed, right? Is the first token that is produced from the decoder. The last token that is fed in is the first token in the decoder. To actually, because you remember the concept of memory in RNNs, right? So this was all driven by the limitations of the LSTM kind of architecture. Yes.
What about like sentence structure in different languages? Like how sentences are structured in different languages, like the words are like the positions are changed.
Yeah, so I'm not a linguist by any stretch of imagination, but I know that what I just told you, including this trick, is pretty much language specific. For example, there are languages which are source and destination, like are or target are absolutely no grammatical patterns correlations. Right? Still, this thing is working to some degree. Okay? It definitely is working very well today with more powerful models. So one thing I want to mention is this, is that feed the tokens in reverse order in the encoder. That's that. The last hidden state contains strongly the first token of the source language that in this example, emphasis on this example, is the first token of the target language bottom line intuition is if you mess it up in the beginning, no hope is there to get a good translation. So that is the rationale of that. Okay. Second is that bidirectional RNNs, LSTMs are used in what is the bidirectionality? Bidirectionality is that there are two thought vectors which are fed to the decoder. One is left-right, and the other is right-left with respect to the encoding. And so this phi will actually be the H3, which is the phi forward, and the phi reverse. And the rationale of that is the following. If I get an example to remember it, so let me just offer an example. Sentence 1. the troops were loyal to George Washington. Sentence two. George Washington is closed to traffic today. In many NLP tasks, in other words, the meaning of the token, therefore its hidden state, is determined by previous tokens. In some others occasions, exactly the same token, meaning, is affected by tokens that follow it. Obviously, this is a bridge, this is a person. So bidirectionality allows us to have this flexibility, right? And for power in the representation of the states being built inside in these systems. And the other third thing I want to mention, and I will close the discussion, is teacher forcing. In other words, I told you what's happened during training. What's happening during training, obviously I have access to ground truth. Okay, but what happens in inference? In inference, I will draw this magenta arrows. Effectively, this is what teacher forcing is, where we are feeding the previous translated token as input to the next instance. I have no ground truth data, so this is basically what I'm going to do. I'm going to take lab and feed it to this. If lab is successful, we'll feed it here. I mean, no matter what, I'm going to feed that input. And so this teacher forcing effectively is, obviously there are many details which I'm leaving on the table. Okay. It's not really my aim here to dissect fully these architectures, but just to give you an example of some applications that can be built with simple networks. During inference, we feed the ground truth via the decoder inputs. During training, we feed the ground truth via the decoder inputs. Okay, and inference, during inference, we feed the previous predicted tokens. One thing that I want to mention in passing to close this kind of discussion is that evidently there is one optimizer that runs a show for both encoder and decoder at the same time. So the thought vector is changing as the training progresses, right? Depending on how good the translations are. So when I said earlier that one thought vector drives the translations, well, this thought vector is obviously changing and reaches a point, right, in space, given the star values of all the parameters involved in the encoder at the end of the day. So during inference, obviously you have frozen weights, everything, right? During the training, one process drives parameters over here. Back propagation happens over the whole chain, decoder and encoder. Are you following? All right. So with that said, I want to spend not with equations. I want to spend one discussion. Yes.
How do you decide the length of the chain?
Okay. So obviously, I skipped the. Obviously, there is padding. There is a lot of stuff, right? So there is some choices that we are making for every language as we move through batching, right? Obviously, we're building batches during the training process. And during inference, obviously, we have to limit the input sentence to some length. But I skipped all that. If you want to look at this, your textbook, Python textbook, has some code, and also I included Python notebooks in my website for this specific Hungarian to English problem statement, which is, again, or LSTM oriented. One sentence on a metric, which is met very frequently on NMT, Neural Machine Translation metric, for Blue, which is also the name of my dog. Okay. This is a good metric to know. Okay, so we have in Neural Machine Translation, obviously, we have benchmarks. Now, one of the limitations of this course is that we don't have a lot of engineering kind of details, right? I mean, this is delegated to some kind of books that typically I'm sort of either assigning as projects or assignments or whatever for reference. But there's a very big chapter called eval, evaluation of models in general, right? Especially natural language processing are a big kind of deal. And there are all sorts of benchmarks, right, that people are evaluating, as we know, all of this kind of neural models. So one of the ways that the benchmark is obviously defined is that there's going to be some reference translations, let's say, from humans. And there will be some translations produced by the NMT model that you have deployed. So by C, I mean the NMT model that is being deployed. So this is the sort of translation. Let's assume the translation is the plain blue from, or flew in from Athens, let's say. This, let's say, the translation. This C stands for the model. And we have humans who are providing a set of reference translations, as we call them. The plane took off from Athens. Another final translation, the plane departed from Athens. So there is some kind of a source language which is foreign to us, and that we don't have to know it. Some sentence that people translated, and also the computer translated. So the metric that is kind of very common to come across, Blue, measures similarity of C and R, that is, using n-gram overlaps. I'll tell you how this is done with you using an example. Let's assume that the n-gram is simply bigram, two letters, right? In this case, two tokens. So we will convert now the translation of the computer into segments of two tokens. Okay, so the plane is one token. Plane flew is a second token. You get the idea. Flew in from Athens. So given this kind of segment, you go and look up the reference translations that the humans did, right? And assign a true positive when we see this diagram being quoted in any of the two translations. Is this a true positive or a false positive? It's a true positive. So this guy will be a true positive event. Plane through, false positive. All the others, except from the last one. Okay, so we have two true positive events, two false positive events, and this blue has the notion of precision as we already have met it. So the precision is obviously the ratio between true positives, true positives plus false positives, right? So a true positive event, just to explain it formally, there are the n grams in C that are also in R. And the false positive, the negative n grams in C that are not in R. And evidently, this kind of metric here is 2/5. This is the basic definition of blue, but obviously the actual definition of blue, the actual metric, is more complicated than what I'm presenting here, because in translation, the machine can play also a lot of tricks. Like, for example, it can present the translation, the plane, and therefore artificially increase the true positives. And obviously, that's not good news for a simple metric such as this. And of course, there are many others. I've not cataloged all the metrics across the NLP domain, and also what work needs to happen now to get to at some point to some kind of qualification of language models. You probably ought to be picking up a frozen language model, maybe a compact one, and running over the evals, as they call them, across all the definitions and provide some definitions of each eval. This work is still happening on the website. But since I saw it in front of me now, I thought to at least tell you something about my dog. All right, so any questions on this metric? Yes.
Why did he say that's an LSD? Said it's a trivial.
A trivial LSTM, yeah. Same thing. Obviously, in the transformer architecture, you have cross attention thing happening in the architecture. We'll not see cross attention here in this course, but in some other courses I'm teaching, they are present because we are dealing with sequence models and things of that nature with transformer models. Okay, so what I'm going to do now is we have half an hour. I'm going to introduce the transformer architecture. And I say introduce because it will take us some time to go through it. I'm going to go slow now, and so that everyone is on the same page. So Okay. So the transformer is going to involve two things for us. It's going to involve two things. Yeah. First of all, yeah. Let us start with the RNN. I'm trying to find if I have notes for the how to start it from RNN rather than directly. Yeah, let's start like this. Okay, so the first step that we will do to introduce the transformer kind of architecture is we are going to eliminate the current connections of RNNs. In other words, we are breaking away from the strict requirement to be able to form the hidden state wrong. We are breaking away from the requirement to form the hidden state HT minus 1 only after we have formed HT minus 2. That requirement is gone. This means that there is a significant parallelization that's going to happen, and all tokens now can be fed straight into the network architecture, whatever that is. So within limits such as the GPU memory. The impact of that elimination, and when I say the elimination is evidently here, this is where is the language model here. The elimination is this guy over here. These connections are now gone. However, the fact that we had connections and we're forming these hidden states in sequence, right? We didn't have to encode that this token is before this token, and so on. So the positional information of the tokens were innate in the architecture itself. Because only when the input is t minus 1, forming state, let's say, ht, right? So ht minus 1, then the input is inside this kind of state. Now, if we process them in parallel, we have to encode that positioning information. Okay, so it's a byproduct of that. It's not typically a big deal. So we will need to write it down, though. We need to inject positional information of the input tokens. Something which is many people refer to is transformers are permutation invariant. Okay. Invariance is a very big deal in general in AI. In the whole field of computer vision is based on building representations which are invariant to some transformation. Okay, but the context that the invariance is being quoted over here is that either I permute the tokens or not will result in exactly the same output if I don't have positioning. So we'll see how that will be done. not now, later. I'm not going to start with position information because it's immaterial to the main stage of the transformer, which is the attention mechanism. So one of the key aspects of this architecture are going to be driven from what we call the attention mechanism. So let's write down what attention is in broad terms before we progress into specific discussion. I'm going to, in fact, suggest that the transformer is going to, architecture-wise, let me write. We have inputs, X, that will go first through the attention mechanism. And then they will go through some form of compute to provide the outputs, the predictions, and so on. Right? So it is really the attention mechanism which changes. This attention mechanism will change the context-free representations we built a few moments ago, right? If you remember, to contextual embeddings, which means in our lecture over here, the blue vector that we left the bank will now be moved into many different places. Depends on what words show up in what we call the input context. Let's say the sentence that bank is part of, for example, in very simple terms. In fact, we may bypass altogether the context-free representation and feed one-hot encoded vectors that are going to be contextualized by the attention mechanism. Of course, we need the positional embeddings as well, right? But we are bypassing this complication for at this point in time. Okay, so let's focus now on the attention mechanism. So the attention mechanism, let's see. This is the first part of this discussion, which is very general. The second part of the discussion is the attention mechanism. Okay, let's see. I have 3 sentences, so I'll use some sort of examples to motivate the discussion about the attention mechanism. So first sentence is, I love bears. Second sentence is, she bears the pain. Third sentence is, bears won the game. So you probably noticed the token bears in these 3 sentences. The first one, let me color it orange. Second one, green. Third one, this guy over here. Same token, 3 different meanings. The first meaning is that of an animal. Second meaning is that of tolerance, let's say. And third meaning is that of sports team, because I'm sure there must be a sports team somewhere here. For bears. Okay, so what we will do in the attention kind of mechanism is to take the bears, as I said, and map it into 3 different places in the d-dimensional space, which is now is contextualized d-dimensional space. Okay, so in order to do that, we have we can start with some simple mechanism, trivial mechanism, that intuition of which is quite important, though. We are claiming that the meaning of bears in the first sentence is going to be contributed most by what other token? The meaning of bears in the first sentence is going to be contributed by love. In the second sentence, pain is going to be the contributing token. Third sentence, game is going to be the contributing token. So, in this attention mechanism, simple version of the attention mechanism, we will recognize that and we will build this mechanism via the simple trivial thing that we haven't done much in this course, but something like dot product, probably hopefully you remember after 6 months into the future. So you can rest assured that this is going to be the mechanism. So we have, we're going to build X as a matrix that is going to be, in general, D by capital T, and this is going to be called the context size, and this is going to be the embedding space. For our case, D is going to be to 4, and T is going to be equal to 3. I will use small dimensions in order for us to understand what's happening, obviously. In reality, T is into the hundreds of thousands, potentially, right? And D is into hundreds, or even thousands. Depends on the model. Okay. So let's see. As I suggested, I will model the impact of one token to others, or in general, the 3 tokens to all 3 tokens with each other, in other words, via the dot product. Because at the end of the day, they are vectors, and being vectors, if one token is able to influence a lot the other, the dot product will be larger than others. Okay? That's the intuition again. I will define this S matrix, which is evidently now is huge. Well, now it's not huge, but in general it's huge, it's T by T, right? That is going to include what we call this matrix are the attention scores. Obviously, the scores are whatever the dot products are. And we will borrow from our portfolio of that we have seen of units, a block called softmax, that we typically use for producing output posterior probabilities. But remembering that is an excellent normalizer, we will use it to normalize the scores to become values between 0 and 1. So what we'll do, we'll apply softmax row-wise for every of these scores, And therefore, we have now some value between 0 and 1 that designates how much one token can impact the other. Okay, so we will apply that, in fact, as follows to produce, which are another matrix, which obviously is equal to 3 by 3, the A11, A12, A13, and so on, A33, such that this matrix, by the way, is going to call attention weights, and is going to, by construction, every single attention weight is greater than or equal to 0 because softmax has e to the power of something, and summation from j is equal to 1 to capital T, A I j is equal to 1 by construction. So with this attention weights now, what we do, we are going to use the attention weight to take car, bank, whatever, the context-free token vector and map it to a different place in the d-dimensional space. So if, and this is something that you can remember out of all attention mechanism discussion, this is the diagram you need to remember. Okay? So we are going to revisit this, but if xi is the initial token, which is context-free token, we are going to produce an xi hat at the output of this attention mechanism, obviously in a different place in the d-dimensional space. And the entity that is going to cause this displacement, this shift, is called the self-attention mechanism that is simply forming the y hat as summation from j is equal to 1 to capital T, Aij, xj. Other displacement, yes.
A I J is equal to 1.
Summation.
What's I?
I,
Like,
the row, I and j. Rows and columns. We are going to do that for all input tokens. So in matrix form, we are forming a matrix x hat, which is softmax of x transpose x, or simply ax, where A is our attention weight matrix. We call it self-attention because the token itself of pairs is affecting itself too. So self-attention. You're not excluding it and only seek assistance from the I and lab, but also the token is participating in the adjustment. So bears start here, ends up here, depending on the other tokens. Depending on the other tokens. So try to translate the equations into English. And this is the end of the simple self-attention mechanism. We are able to do the shift and we can progress with subsequent stages of the architecture. And next time, what we'll do is we'll start from here and see why this may not be the right, not the right, but why we need to complicate things as we typically do. Okay. Yes, go ahead.
We don't have to like mask some like matrix elements.
We will come to that. We'll come to that. The masking and all that kind of stuff will be discussed next time, though. Because right now I'm falling apart. So I am going to close the discussion now. Oh, yes. There is. Don't tell me that you didn't pass it around. Oh, it's there in that guy. This guy has it, which is no person. Okay. All right. Thank you.